reverse.
And that's what
that is X out. To get the same X out, we need a bigger tau. Other questions? Okay, so notice in a plug flow reactor, I start out with a high concentration of reactant. And the concentration of reactant gradually goes down as I move along the plug flow reactor. So if this is the concentration of reactant, say A, it goes down gradually over the course of the reactor. In contrast to the CSTR, I have an inlet concentration, Ca in, and then as soon as I get into the reactor, it drops to Ca out. So the entire reaction here is taking place at the outlet concentration, slowly. Whereas here, we can see, assuming the rate of reaction is monotonic, it's not always in the concentration of A, that here A goes down gradually, and only at the end are we at Ca out. So if the rate of reaction is higher for higher concentrations of A, then everywhere along the reactor, the rate of reaction will be faster here than it will be here. And if it's faster, then I'll need a smaller reactor to get to the same final condition. Let's say, however, that there are good reasons that I need a CSTR. What kind of good reasons could there be? For example, I may have mass transfer limitations. It could be that I have a catalyst, and the reactant has to diffuse through a stagnant boundary layer to get to the catalyst surface, and then has to diffuse inside the catalyst. And if I mix, if I do some mixing, then I can greatly reduce the mass transfer resistance of getting to the particle. So there's a good reason for me to use the CSTR. But I don't want the penalty of having a very slow reactor. So one thing I might try to do is I might try to use two reactors in series. If I use two CSTRs in series, I'm not as good as this, but I'm better than this. Because what happens with two reactors in series? If I make that same plot, so I've got in, out, in, out. Here I've got 1. So what happens is here I drop to Ca1. I stay here for a while, and then I drop to Ca out. So instead of being here the whole time, I have a long section when I'm in reactor 1 where I'm at Ca1, which is a higher value than Ca out. And if the rate function is monotonic in Ca, then this is going to be faster. I don't know where people are today, but we're going to drop the people who don't show up. They continue to get next year. Is there a question?
Yeah. This is assuming non-interacting CSTRs?
Non-interacting?
In other words, the output for V1 is going directly on top of the output of the input of V2. In other words, the level of it.
Yeah. When it comes out of reactor 1, goes into reactor 2. If I mean something else, I'll draw something else. And this is in series. That's what in series means.
So, the plug flow is concentration with respect to location on the plug, whereas that's concentration with respect to time, right?
No. This is as a function of z, and this is a function of position. So here's the position is the pipe leading to the reactor, and this is once I get into the reactor, and once I get out of the reactor. That's what I'm plotting.
So really, three different positions: in, tank, and out.
If you like to think of it that way, sure. There are three different, because of the fact that I am mixing here, everywhere in the reactor is the same, and in the outlet is the same. That's why this is all on, say, a horizontal line. But again, I'm trying to give you a sense of position. There's no time here. These aren't steady-state reactors. There's no time. Steady-state. Okay, so let's just, I'm going to use the blue chalk for a second. Remember I told you here the concentration goes down gradually. So let me draw that in here. The concentration goes down gradually. I didn't really draw that very well. Actually, no, I did. I drew that okay. Okay, so let's notice that the outlet from this reactor is right around here. This is outlet from first reactor. And this is, say, the outlet of the second reactor. And you can see, if we were dealing with, say, I'm doing this for a constant density system, well, it doesn't really matter. What you can see is that this particular curve is a lot closer to this curve than this curve is. That is, if I had a single CSTR, let me use some other colors. This is 2 CSTR. For the how the rate is as a function of position. This is log. And of course, a single CSTR looks just like this. So a single CSTR, this curve, is very different from the blue curve. 2 CSTRs in series is a little closer to the blue curve. How can I get even closer to the blue curve?
An infinite number in series.
But a lot of CSTRs. So let's say I go like this. Then my curve would look something like this. Right, a lot of them. In fact, I'll get closer and closer. So this should remind you of something. It should remind you of a Riemann sum in from calculus. Why is that? Let's go back to these equations here. So if we do CSTRs in series, and I try to look at the taus for the CSTRs in series, then again I'm plotting -1 over RA versus XA. Here I'm going back to X's. So this was just generically the concentrations. But now I want to plot -1 over RA versus XA. And we said, so the curve typically looks like this. If it's monotonic, here's in, here's out. And what we have when we have many CSTRs in series, if you look at this, then what we have is a bunch of rectangles. Where, if you remember, each rectangle corresponds to a CSTR evaluated at the outlet conditions, the right endpoint. So here's CSTR1, CSTR2, etc. And if I make this CA0, then this is tau1, tau2, tau3, tau4, etc., tau n. And what you can see by the limiting process, the limit as the number of CSTRs goes to infinity, and the tau goes to 0, or if you like, the delta x goes to 0, an infinite number of CSTRs in series gives you a plug flow reactor. So I've got the limit as n goes to infinity, and at the same time as x j minus xj minus 1 maximum. So this is the maximum one of xj minus xj minus 1 goes to 0 of the CSTRs, so the sum I goes from 1 to n, tau i's is, for CSTRs is equal to tau plug. And someone anticipated that in the class or two ago. And let's just do a simple example that illustrates that we can do that explicitly. So for example, let's look at an example. We've sort of shown this in general, but let's look at an explicit example. Let's look at n CSTRs in series with first order irreversible reaction. Constant pace. We've already solved that problem. For a single CSTR, one CSTR, we found that C out over C in is equal to 1 over 1 plus K tau. So now for the Jth reactor, so now if I do it this way, so this is in, this is 1, 2, 3, n minus 1, n. So I have the outlet is always one higher number than the inlet to any given reactor. So reactor 1, reactor J has outlet J and inlet J minus 1. So I have, and I'm going to flip this, so I have Cj minus 1 over Cj is equal to 1 plus K tau J. So therefore, if I look at C in over C out, well, in I've labeled as 0 here, and out I've labeled as n. So I have C in over C out is C in over C1, C1 over C2, dot dot dot, Cn minus 1 over Cn. Because the C1s cancel, C2s cancel, etc. And each one of these, I know what it is. So this is just the product, I equals, or J equals 1 to n of 1 plus K tau J. Now let's look at the simple case. This is an example where all the taus are the same, tau J's. So suppose tau J is tau total divided by n. So then I have, so they're all the same. So then I have C in over C out is equal to, well, it's the product of factors that are all the same. So it's just each factor to the nth power. So I have 1 plus K tau over n raised to the nth power. And in this case, I would like to take the limit as n goes to infinity. Now this hopefully you saw in high school. I have 1 plus something over n raised to the nth power. The limit as n goes to infinity. So clearly if n is infinity here first, then I just have 1 to the n, which is 1. If this n goes to infinity first, then I have 1 plus something go to the n to the infinity is infinity. But if I balance them such that this goes to infinity and this goes to infinity at the same rate, then this is the definition, at least the definition I had in high school, of what function. Mom's here? Who took math in high school? Who took the Regents? This was on the Regents. Anyone got high school in New York State? Nobody knows this? You never took calculus? No? This is the definition of the exponential function. This is, before you learn Taylor series, this is the way you define it as a, this is just e to the kt. So that tells me C out over C in is equal to e to the minus kt. It's 1 over this, k tau. This is definition of the exponential function. Okay, so what have we done so far? We've done plugs in series plugs in parallel, and CSTRs in series. CSTRs in series. What's left? CSTRs in parallel. So let's look at CSTRs in parallel, and let's compare. We need a question here. So we want to look at CSTRs in parallel. And in particular, we're going to want to compare if I have a bunch of CSTRs lying around. So I don't want to go build new ones. I have a bunch of them in the basement. And the question I have is, I have this given reaction I want to run. And I would like to use them most efficiently. That is, I have given product specs, and I would like to make the maximum amount of product. So X out is given, and I would like to maximize F. So given V1, V2, dot, 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 Vn is sitting in the basement. And given the product specs, X out, and actually the feed, X in, how should I arrange the reactors to maximize which gives a higher FA in series or parallel? Let's see which one does better. Should we arrange them in series or should we arrange them in parallel? Well, let's do a little bit of analysis. So first, let's just go back to a single CSTR. Now, I'm going to assume I have M of these, because I already used N, a different letter for a change. And X out, by this scheme, is just going to be the same thing as XM, the outlet of the M3N. Okay, and let's see what we get here. The class started 35 minutes ago. One CSTR. Okay, so I have V over FA0 is equal to. So here I'm assuming, and now I'm going to make life easy, I'm going to let in FA, I choose the reference state, so I'm going to let FA0 be FA in. It's the first reactor. So let's look at a single CST. I choose the reference state, so I'm going to choose one that's convenient. V over FA0, here's my CSTR equation. Tau over, I think I did this backwards, this is plug, and this is CSTR. Tau over CA0 is just V over FA0. It's X out minus X in over minus RA out. So this is equal to XM minus X0 over minus RAM, where M is the outlet. Now, if I have only one CSTR, a system with only one CSTR, I happen to call the outlet XM. Okay, and I just want to rewrite this, so I have XM over minus RAM is equal to V over FA0 plus X0 over minus RA0. And I just want to keep that for future reference. So this is a single CSTR with XA0 coming in and XAM coming out, and FA0 coming out. Okay, now let's look at N CSTRs in parallel. Actually, let's do that down here. Let me finish drawing the picture. So here I have FA1, F2, Fn, and here I have x0, x0, and of course all these have to add up to Fa total for parallel. And what we learned here is in order to get the most efficient scheme, whether it's series or plug, I always want to minimize the mixing to get the most efficient scheme here. So I'll do the best when all of these have xm, when the outlet of all these is xm. Any question? Okay, so this is the parallel scheme. And let's see what we get here. What we get is that for all of them to have the same xm, I need Vj over Fj is equal to, say, V1 over F1. The first one, all of them have to have the same V over F, the same tau, in order to get the same xm. So that tells me that Fj, the way I split these up, is equal to V1 over F1, is equal to F1 times V1 over, let's see, Fj is Vj, is F1 times Vj over V1. And therefore, the total F, because I want to compare which one does better, F total for the parallel arrangement is equal to the sum of the Fj's. And that's equal to F1 over V1 times the sum of the Vj's. Which is just equal to F1 over V1, V total. And this is, as we say, F total in the parallel arrangement. And now the question is, if we have n CSTRs in series, can we do any better? Or are we stuck doing worse, or the same? So let's look at n CSTRs in series. Here we have our picture for n CSTRs in series. Okay, and so for n CSTRs in series, let's go ahead and try to analyze this. All right, well, we know, as we said, for the, so n CSTRs in series. So we know that if we go back to our equation for CSTR, tau over CA0 is V over F. V over F is this thing. So V over F, Vj over Fa. Now since these are in series, I have the same F. F total is going to everything. So I have F total series going into all of them. And that's, I'm going to choose that as my reference. So Vj over F total series, as opposed to F total plug, is equal to Xj minus 1 over minus Raj. Because remember we said that the Jth reactor has an inlet J minus 1 and an outlet J. And since it's out minus in, it's J minus 1 over minus Raj. J minus 1 over minus Raj. Okay, so let's add these up. This is for the Jth reactor. If I add them up, I have V total over Fa total series is the sum of Vj's over FATS, J equal 1 to N. And that's equal to the sum, J equal 1 to N, Xj minus 1 minus Xj minus Xj minus 1 over minus Raj. Just for fun, I'm going to pull out the last term of this sum and write it out explicitly. So I'm going to write this as the sum j equal 1 to m minus 1 xj minus xj minus 1 over minus raj. And the last term I'm just going to write explicitly. The last term is xm minus xm minus 1 over minus ram. Now you might say, why am I doing that? I'm doing that because I know something about this ratio, xm over minus ram. xm over minus ram is just this thing. So I can plug in for that. And let's see what I get. So this is equal to the sum xj minus xj minus 1 over minus raj. And then I have a plus something. So here I have xm over minus rm. And xm over minus rm I could replace by x0 over minus ra0 plus v over fa0. So the v over fa0 I'm going to move to the other side of the equation. And this is one reactor, so it's reactor 1. And what am I left with over here? Here I'm left with xm minus 1 over minus ram. And then I have a plus x0 over minus ra0. And let's just see if I have any mistake here. Yeah, I made a little mistake. This is minus RAM, so this should be minus RAM. When I copied it over here, I put a 0 in here instead of an M. So I have an x0 minus xm minus 1 over minus RAM. Where I plug in for xm over minus RAM, xm over minus RAM as x0 over minus RAM plus v1 over fa0. And the v1 over fa0 I brought to the other side of the equation. Okay, so let's notice that I can do a little algebraic trick here. I can notice that x0 minus xm minus 1 could be rewritten in the following way. x0 minus xm minus 1 can be written as x0 minus x1 plus x1 minus x2 plus x2 minus x3 plus dot 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 plus xm minus 2 minus xm minus 1. Is that clear? All I did was I added 0. I added and subtracted x1, I added and subtracted x2, etc. And then I could put parentheses around terms here. And if I do that, I notice that this is equal to the sum, or minus the sum, j equal 1 to m minus 1, of xj minus xj minus 1. It's always one minus the other, and the minus sign I put in so I have the one with the bigger subscript subtracting the one with the smaller subscript. So notice a sum j equals 1 to m minus 1 is exactly what I had here, so I can combine these two. So this is equal to the sum j equal 1 to m minus 1, xj minus xj minus 1. It's exactly what I had up here. But now I have 1 over minus raj, which is this. And then I have the minus sign, 1 over minus ra. Is that clear? Okay, so now I'd like to rearrange this. So let's bring this to the other side of back to the other side of the equation. I don't know why I brought it to this side. I could have left it on the other side. So let's leave it there. But now I'm going to divide by that. So I'm going to have Vt over Fats divided by V1 over FA 0 is equal to 1 plus the sum plus FA 0 over V1 times the sum j equal 1 to n minus 1 xj minus xj minus 1 times 1 over minus raj minus 1 over minus ram. And let's notice something. First of all, what's FA0? This particular analysis I did for the first CSTR in this particular situation. So here I took n CSTRs in parallel. Yeah, remember I looked at one CSTR. When I looked at one CSTR, this one CSTR we can think of as the first CSTR. So this first CSTR has a V1, it has an FA1 and X. Well, let's see. Is that? Let me just make sure that's right. I'm not sure that's going to be correct. No, I think that's okay. It was the first CSTR here, so this was V1 over FA1. So this FA0 should have been FA1. So it was going into the first reactor here. So this FA0 is FA1 over 1. Well, notice here I have a VT FA1 over V1. VT FA1 over V1. So this whole thing is nothing more than FA T parallel over FA T series. In fact, we'd like to find out which one is higher, so we just have to examine this ratio. And let's see what that ratio is going to be. Now that ratio is 1 plus something. So if this something is positive, then I could do better with the parallel arrangement. If this thing is negative, I can do better with the series arrangement, because then the thing will be either greater than 1 or less than 1. So let's examine all the factors here. Xj, first FA1 and V1 are both positive numbers. So this is clearly some positive quantity. Xj, the outlet from a reactor, is generally going to be higher conversion than the inlet. So this thing is always going to be positive. So let's look at this quantity. Minus Raj and minus Ram. If A is a reactant, then minus Ra is positive. Now, in reactor M, A has the lowest concentration, because it's the last reactor. So the rate is the slowest. If the rate is the slowest, 1 over the rate is the biggest. So it says that this quantity is always greater than or equal to this quantity. So this thing is less than or equal to 0. As a result, if I take a plus times something that's 0 or negative, what do I get?
Negative, right?
Negative or 0. So this whole thing is now going to be less than or equal to 1. So what does that tell me? Which one can I do better with? Series. So I should hook them up in series, because the series arrangement is always going to be at least as good. So we've learned something. The series, if we have the reactors lying around, we should hook them up in series, as long as the rate function is monotonic. If the rate function is not monotonic, then I have to re-examine and see what the sign of this thing is. Are there any questions? Okay, any questions? Let's ask another related question.
Okay, so the expression that you have with the rates, I think I got lost in the algebra, but I wanted to know, is this based on the parallel or a series configuration?
It's what based on a parallel series?
The result that you get from the difference in the RA, is that based on parallel or series configuration? Because
Okay, right in the beginning, and including every line of the notation, I have a S here, I have an S here, I have an S here, I have an S here. What do you think S stands for?
no, I don't know.
And I wrote it on the blackboard. N CSTRs in series. I don't think I can make it any clearer. I wrote series here, S, 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 S. Are there any other questions? Okay, let's ask another related question. So in this case, we have the reactors lying around and we want to know how to hook them up. Now, let's say the reactors are not all the same size. We know that series is better than parallel, but there are lots of ways of hooking them up in series. The reactors are in different sizes. So I put the big one first, the big one last, the little one first, the little one last, the little one in the middle, the big one in the middle. How do I know the best thing to do? And in general, I might have a complicated rate function that may not be simply monotonic. So how would I go about doing that? Okay, well, so in what order? Good, I hook the reactors. All right, so let's go back to the design equipment. And let's look at the design equation. I've got tau is equal to. And do I want to look at it with constant density? Yeah, no, with non-constant density. So I've got tau is equal to CA0 x out, or xj minus xj, tau j, xj minus xj minus 1 over minus RAJ. So let's just rearrange this. Minus RAJ over CA0 is equal to xj minus xj minus 1 over tau j. Now, when I say how should I arrange them in series, let's say, I need to make the question more specific. What's my goal? Let's look at one case, say, where F is fixed. So I have a flow rate, and I want to get to the largest x. So for F total series fixed, maximize x. I could change it around and do the other one, but I want to look at this particular case. So let's see what this equation tells me. Let's plot minus RA over CA. And let's plot that versus x. And then I get some sort of curve. Now, if the function is monotonic, then the lower x, do I have more reactant or less reactant when I lower x? Did I wake you up?
Yeah.
Am I talking to myself here?
Have lower x, you have more reactant.
Lower x, I have more reactant. More reactant, if I have a monotonic rate function, means faster or slower reactions? Faster. So in general, if I have a monotonic reaction, it's going to be highest here and go down monotonically. Now, of course, it could be a complicated function, and who knows, it could be some funny-looking function. It's going down. I've drawn it going down, although I drew it not monotonically. It doesn't have to be monotonic. If it is monotonic, that's great. But let's see what this tells us, this particular equation tells us. If I have a bunch of reactors, I can let's say I choose a particular arrangement. For any given arrangement, so I label this reactor 1, this reactor 2, this one reactor 3, etc. For any given arrangement, what does this tell me? I start out with some x in. Then the outlet from reactor 1, x1, where is it here? x1 related to x in is related by this equation here. So it says, let's see what's known and what's unknown. If I start here, x in is known, because that's the inlet. Tau is known, because F is known and the volume of the reactors are known. CA0 is known. That's just the reference state. So what's unknown? What's unknown is the outlet, xj, and the rate at the outlet. Yes?
So all your reactors have to have the same volume?
I didn't say, no, they're all, if they all have the same volume, there'd be no question. In series.
The volume is known. So you know the difference.
Okay, I know the names of the people in this class. Does that mean everyone in the class has the same name? That's the logic you're using. Because I know the volumes, they have to be the same. Because I know everyone's name in the class, that means Allah's name is really Omar also. And Robert's name is really Omar. Okay? Okay, so all right, so let's see what we have here. Let's stare at this for a second and see if we know what we have. Okay, so let's rewrite this. This is equal to minus xj minus 1 over tau j plus xj over tau j. All right, so this is the equation of a straight line. Okay, so I have y is equal to something times x plus a constant. So the slope is 1 over tau j. So if I want to get to, this is, say, y, this is the slope m, x plus b. So if I know xj minus 1, and I know that at xj minus 1, I know what minus raj is. Well, I'm sorry, at xj minus 1. If I start here, then this says in order to find xj, I just move along a line that has a slope 1 over tau j. Over tau 1 until I hit the curve. And when I hit the curve, then that's going to be minus raj, minus ra1 over ca0. And then when I move down, I'm going to get x1.
This curve, wouldn't you have to do the experiment first? So you'd have to put them into...
Do the experiment. What is the experiment?
Place them in a certain order, and then, I mean, in order to get the
No. The chemist gives you the rate curve. You have the rate as a function of, we determined it earlier in the semester. You don't need multiple reactors to get the rate curve. You need a single batch reactor to get the rate curve. And once you have the rate curve, then you can, for any given arrangement, you can then proceed stepwise. For reactor 1, you know 1 over tau 1, and then you move here, and then for reactor 2, you know 1 over tau 2. And that gives you minus Ra2 over Ca0. And that gives you x2, etc. And then you march along. And then you find, for any given arrangement, you find xn. And then you can try different arrangements. And you can see which one does the best. And then we'll look at this case for an nth order reaction and see what you get. That one you can solve in general. But if you have a complicated rate expression, one way of doing it is doing it this way. Are there any questions? Okay, well, why don't we, let's just look at that for a second and make sure we're happy with it.